All right. Thank you very much for the introduction. My name is Daniel Alaez, and I'm glad to be here participating in this great symposium. And today, we will be presenting the work I have developed with my colleagues Daniel Leandro, Miquel Bravo, and Jesus Villadangos. And first of all, I would like to start my presentation by apologizing because I know all of you are great experts in fiber optic sensing, and I'm certainly not. I'm more interested towards the applications, as I will try to show you now in the presentation. So if you have any questions regarding very technical aspects of fiber optic sensors, maybe Daniel is the person to ask. All right, so that said, I will start with the presentation, which we have titled Direct Measurement of UAV Propulsion System Performance Using Fiber Optic Sensors. So to give you a little bit of background, I'm with the Department of Statistics, Computer Science and Mathematics here at the University of Navarra. And my lab is just upstairs, so if you want to check our experimental setup later, you are more than welcome to visit it. So what we do in our group is we develop, we test, and sometimes fly unmanned aerial vehicles, often called drones. And we try to design them both for indoor and outdoor applications, as I will show you later. Our group has a lot of industrial transfer with companies here in the sector in Navarra, but we also do a lot of research just for pure research. And we often aim to participate in academic UAV conferences and competitions such as the IMAF, which is the International Micro-Aerial Vehicle Conference and Competition, which is organized yearly. And last year we were lucky and we placed third in the outdoor competition. So that said, when we are working on a new UAV design, we frequently aim for some design goals. Most of them are commonly maximum stiffness over weight. We aim to carry large payloads. We also like to fly for longer, so maximizing the autonomy, but also maximizing the range. So the longer and farther we can fly, the better. So if we take all of these goals together, we often have to optimize for a single parameter, which is called the disk loading. So the disk loading is the relationship between the aircraft weight and the rotor disk area. So how large or how heavy is the aircraft over how large is the propeller. So for optimizing all of those goals I've mentioned, we typically aim to reduce this disk loading parameter in order to improve efficiency. So what are the options here? Well, there is not much to do. We either reduce the aircraft weight or we increase the disk area, which is the same as saying that we will increase the propeller size. But with this solution comes a big problem. So whenever we get a small propulsion imbalance, which is, for example, a poorly balanced propeller, it can produce larger vibrations. And the lighter our aircraft is, the more impact we get from those vibrations on the control of the aircraft. So when we get those vibrations, since we are basing our control on the feedback from the sensors, we are applying poor control. So we try to minimize those vibrations. Let me introduce you to an industrial use case so I can give you some context. Here's a crash drone of a company we work closely with. It's a spin-off from the University of Navarra. And they typically perform power line inspection. So they fly their vehicles across power lines and they take photographs, LiDAR measurements and all, so that they can gather data of the state of the power lines. So for that, they require multiple payloads. So they typically carry LiDAR sensors, multispectral sensors, high-resolution visual cameras, amongst others. For reference, each mission can be more than 6 kilometers long on a single battery. And if you do the multiplication, they have multiple drones flying at the same time every day for a few missions of 6 kilometers long. So if you multiply statistically over a year, you get anything that can happen will happen. So any type of accident that you may imagine, it happens. And the downside of that is that whenever they crash the drone, they not only break the drone, but they also break the payloads. And typically, if you sum up all the payloads, sensors, the drone itself, manufacturing cost and all, it can go as high as 100,000 euros. So that's a good reason to try to prevent those crashes. But how do we measure those vibrations that I have mentioned? Well, typically, here you have the common control loop of most of the quadrotors or the multicopters that we fly. And here you see two control loops, one outer loop, which is in charge of the position controller. So that means where we are, where we want to go. And if we want to go there, we need to apply some angles to the aircraft, so the aircraft moves there. That is an input to the inner control loop, which has an attitude controller, which is in charge of, if I want to be in this angle, well, now I'm here, I need to do like this, right? So for that, we apply a control to the rotor speeds, because the way we change our attitude is changing the speeds of the motors. And that is applied to the aircraft does whatever it needs to do, and then we measure the feedback with the sensors. So we want to be here, we are here, so we apply a correction, and so on. How do we measure from those sensors? Well, typically, the flight controller carries an IMU, or multiple IMUs, inertial measurement units, which are equipped with gyroscopes and accelerometers. What's the problem with this? Well, we only have a single IMU mounted on the middle of the aircraft, inside the flight controller, so we cannot get distinction between individual motors. So we just get like the aggregation or the sum of all the vibrations induced by different motors, propellers, and everything. As a solution to that, there are some RPM sensors, some speed sensors that can be mounted on individual motors, but they typically rely on optical measurements. You emit a light, you have a reflective tape or something on the motor, and you get the reading, so for the speed of the motor. Or we rely on electrical current variations, so we are measuring the change of the electrical current applied to the motor. As you can imagine, those types of measurements are very subject to electromagnetic interferences and varying light conditions. We cannot always perform good measurements of that. So here is where the fiber Bragg rating sensors come into place, thanks to our colleagues who suggested using this kind of sensors, where we get some of the advantages to overcome those problems. As you already know, they are not sensitive to electromagnetic interference or light changes. They are easy to embed on different surfaces because they are light and they are flexible. We can get absolute readings, so we do not only measure short time changes, but we also get how the surface changes over time, over long periods of time. And as another advantage, having the ability to install multiple sensors wherever we can or wherever we want, we can provide individual information for each motor and propeller. So in order to test that, we conducted an experimental setup where we used a conventional thrust stand, which is like a motor benchmark tool that we bought from RC Benchmark. We installed a calibrated optical RPM sensor, of course, in a controlled laboratory environment, so we can get precisely the RPM of the motor and the propeller. We installed some temperature probes to measure temperature changes over the experiment. And the RC Benchmark thrust stand contains several thrust and torque load cells, conventional load cells. So we can measure thrust, torque, the weight of the compound, and all of that. And we installed the same motor that this company typically use for their flights with a conventional carbon fiber propeller, a 15-inch propeller, which is quite large for a multicopter. And we decided to play 3 FPG sensors, as you can see marked in red and blue in the image, to perform the measurements. So let's hope it will load. We have a small video here. Okay. So we did this in our lab upstairs, which is quite small. And I do not suggest you to conduct this type of testing in the lab because it's quite scary. Right now it's spinning at idle, so it's like minimum speed, and you don't want to be close to that. Just for reference, so you can see how we mounted it. Okay. So for the experimental settings, we set an automated by code experiment where we have a 60-second acceleration ramp followed by a 60-second deceleration ramp. We measure strain at 1,000 samples per second, so 1 kilosample per second. And on the first test, we just measured the perfectly balanced propeller. And then we added some small duct tape perfectly adhered to the surface of the propeller. So we can create a slight imbalance on the propeller, but not affecting the aerodynamic performance of the propeller. So it's perfectly adhered to the surface. So this duct tape was weighted under 0.25 grams. We cannot measure that way very accurately, but it's on those numbers. And what we did is, between experiments, we started placing this duct tape close to the root of the propeller, so the center point of rotation, which is the one that technically should generate less vibrations. And then, on the following test, we kept moving the duct tape towards the tip of the propeller, so from the center of the rotations to the most outer part of the propeller. So we measured with the load, with the thrust stance sensors that it included, and it was laboratory calibrated. And we performed a comparison with the FPG sensors. So for the experimental results, we first noticed that we were able to accurately represent the thrust measured by the reference load cells and match them with the strain measured by the FPG sensors. And as you can see, the match is almost perfect, which means that it seems to be working. And later on, we measured the frequency. We performed a frequency analysis over time, and we found that the reference optical sensor speed reading perfectly matched with the highest intensity reading from the frequency analysis. And as you can see, that means that we can successfully measure both the thrust and the rotational speed just by placing those FPG sensors on the arm of the propeller, not even on the motor nor the propeller, just the arm. So for the second experiment, as I mentioned, we placed this duct tape from the root to the tip, and we tried to measure how much amplitude had this vibration over the entire setup of the experiment, so that we can see if we are able to capture any imbalance in the propeller, and maybe even capture where it's the imbalance. So this is the reference for the balanced propeller. So this is the original propeller. As we throttle up, we get some more vibration on higher speeds, and then we decelerate and it reduces. But as soon as we unbalance the propeller and start moving the duct tape outwards, this vibration becomes larger and larger and larger. So There you can see the amplitude envelope for all the tests that we conducted. And as you can see, we can associate the position of the duct tape with the amplitude of the vibrations that we read, which means that effectively we can measure how imbalanced this propeller is, or maybe even where the duct tape or the imbalance in a future damaged propeller may be. So the key findings that we found on our initial test is that the thrust associated with the slow dynamic strain and the RPM associated with the fast dynamic strain can be effectively measured using those FEG sensors in a UAV. And also we can characterize the propeller imbalance using this type of FEG sensors. So the obvious question, what's next? Well, we have conducted experiments on a controlled thrust tank on the laboratory. Now we want to take it outside. We want to fly it. So for that, we first need to integrate the FEG sensors on the actual aircraft. So we will be placing on each of the arms of the aircraft. Then we are developing a real-time onboard signal processing software so that we can gather data in real time and generate a good data set so that we can analyze those effects. And finally, just fly it. Perform a lot of flights, gather the data, analyze, and see if we can extract any patterns. The question is why? Why would you like to fly those expensive sensors and maybe crash them? Well, as I mentioned, we would love to be able to monitor the structural health of the aircraft so that we can gather maybe if a carbon fiber rod is bent, if it's cracked, or if a bolt is loosened. We also like to extract any motor failure. So if a motor is about to fail, maybe we can early detect that so that we can prevent the aircraft from crashing. And also we can detect, for example, if a propeller has hit, in the case of the power line inspection, some tree or some branch and has caused some damage, maybe we can detect that. So in summary, we want to anticipate any possible failure points so that we can increase the operational safety of the aircraft in order to prevent crashes. Oops. So that's it for my presentation, and thank you for listening, and I'm open to any questions that you may have.
Let's start the speaker. We have time for a few questions, please.
Thank you for a nice presentation. Very interesting.
Thank you.
Sorry, maybe I missed this. Where did you put the fibers?
Okay, so we decided to place 3 fiber sensors on the arm of the aircraft.
Okay.
Yeah, one on the outer side, or 2 on the outer side and 1 on the inner side, so that we can compare if it's in compression or in traction.
How do you decide to the position? So I mean, a loop is better.
Mm-hmm.
Have a larger strength.
Yeah, maybe that's a question for Daniel, maybe.
Closer to the root, I think you get higher information, right? But at that time, we just wanted to check if we could have enough information to be measured. That's why we put like 2 red to actually check how the amplitude was reduced to the distance. And on both sides, just to compare, just one was working in traction and the other was and actually, the results are only for one of the sensors. We actually could have included all 3, and all 3 gave the same data because the data is not based on actually the amplitude or if it's working on traction or compression, but on the changes, the frequency analysis and so.
And so also I'm interested in a way to detect the unbalance. Now so you are looking at
Mhm.
check it.
Yeah.
And did you check frequency, FFT? Or?
Yeah, we have a lot of data from the frequency analysis, but unfortunately we could not include all of that into a single presentation. But we have the data, and we are planning on using it for a future.
And also, this is a comment. So my suggestion is,
Mhm.
so if you look at the correlation between sensors, and also you can maybe look at the correlation between input and ESGs or duty ratio or something like that. So and output. You get something.
Yeah, exactly. When we perform the experiments, we not only store the data from the FEG sensors, but we also store the data from the test bench. So we have all the data together, and we can do the processing. So, for example, we measured that the speed relationship with the throttle signal was not linear, because indeed in Brussels motors with aircrafts it's like polynomial relationship. So we saw that in the data as well. Yeah.
I used to do study at quad rotor 25 years ago.
All right. Thank you very much.
Any other questions for the audience? Please.
Yeah.
So this is very nice, actually. What happens when you add the next propeller to it? Would your sensor pick up the data from both of them? Would you be able to distinguish?
Yeah. The idea, or what we are installing just right now, and we are installing it next week, is to place the sensors on each of the arms of the quadcopter. But we are also going to include a few sensors on the core of the aircraft, so that we can analyze data separately and then aggregate it together, so that we can maybe filter out the vibration induced by one motor to the other, and so on. But that's a very interesting point.
It's all mechanically the same.
Yeah, technically, yeah.
You just said all the three sensors give same data. So
That's for the same arm, but we have a lot of joints. So we have bolts in the middle. We have some plates which are subject to some bending. So that's something we indeed want to try. But we cannot do that just on a single thrust test stand, so that's why we want to take it to a real flight test. Yeah. Thank you.
Any other question? Please.
Just a curiosity, which kind of interrogator do you use? An easy one or the
Yeah, that's for me. Yeah, we used an FPGS high-end FPG interrogator, so it's quite huge. We were connected to the lab. But for the flight test, of course, we are not using that. We are using a very compact one. We will work on first window, I think, FPGs. So the interrogator are more compact, also cheaper.
Yeah.
Oh, yeah.
Yeah, the interrogator we are using is about 150 grams, which is more than enough for us. We can carry up to 4-5 kilograms. So.
No. From P-Sense.
The X1000, I think. X1000 is the model. Yeah. Oop, sorry.
But for example, just one more question. Probably I'm wrong. I'm not sure. But in the crane world, the drones are driven by fiber optics, isn't it? So I mean, they are linked to fiber optics.
No, we are actually carrying the entire setup.
In the crane world, I think. In the crane world, I was reading that was linked by fiber optics directly the drone. So probably you can put all the bracket in there, and then you can have the control here, as Professor Lopez has. So you can, in real time, to monitorize everything on the drone.
Yeah. We also wanted to test in our flight lab with indoor flight, because we also develop indoor flight drones. And for the testing in the lab, we actually, instead of using a battery, which is sometimes dangerous in the lab, we use cable. So we can drop the fiber with the cable and fly indoors. But we have many more problems arising with that. For example, positioning in indoor environments. which are outside of the scope of the testing we want to do. We need to position ourselves indoors, and that's on another totally different subject.
Another level, okay.
Yeah.
Thank you very much. So let's talk again.
Thank you.